we're still working with base extension. We're going to prove a very important isomorphism, so let's prepare for that. Firstly, let's prove this base extension is actually an object satisfying universal property. Let M be an R module. Then for any S module N and R module, R linear map from M to this S module N, there is this unique S linear map which factorize this phi. Let's call it phi S from the base change from the base extension of M to N. Let's draw a picture. So the basic canonical map is base extension. We claim that it has some universal property, which namely any R linear map to a S module factors through this R linear map of S module. So this is the doorkeeper of this R linear map of S module from M. In other words, as Kinsconar said, this particular R module, the R linear map from M to S module, explains all other R linear maps from M to S modules. Let's prove. First, prove the uniqueness and then the existence. Okay. Uniqueness. So if you make diagram commute, then obviously you should satisfy phi of S acting on S. So this is R linear. This is R linear. Sorry. So acting on any element Okay, I didn't explain it sufficiently clear, so claim there is a unique S linear map. So if this is S linear, then things become easier, because as as S module. So this is the same as this, and S linear tells you can move this outside. Once you got this, things become clear. This is just by the commutative diagram, the same as phi m. And so we're done, which means phi determines uniquely phi s. So the existence. So obviously we are going to define it this way. So we want to define it this way, right? But the question is, of course, this is a problem of tensor product. You have to construct a bilinear map. We're going to construct a bilinear map S and M to S tensor phi m, and this is S bilinear. Wait for a while. Not S bilinear, because M is not S module, this is R bilinear. So this implies there exists a map tensor over R to N. Let's call this phi S as tensor M mapped to S phi M. And one, save that. Notice now it makes sense to talk about S linear. Just define is S linear because the S module structure is only on the first component, so it's compatible. And one checks this mixed diagram commutes. Okay, second part of the exercise. This is the main part for today. So we have constructed what is phi S. From this S linear from S tensor with M to M to whatever S module N. Well, phi is here from R linear from M to N. And then this universal properties already tells you that you have this bijection. Let's write down what bijection. So let M be an R module and M be an S module. The function phi map to phi S, just defining the last exercise, is an S module isomorphism from R module M to N to S module linear. So here, mysterious thing is this a S module? You say this is S linear isomorphism. Remark. So you just scale it on your image. Okay, give it as module structure. So let's write down the proof of this. We first check this is as linear. So you can call this function S. So if you have phi 1, phi 2, and then you apply to S. Question is it phi 1S plus phi 2S? For example, let's check this. What you do is both sides are just maps, so you check it on generating tensor or elementary tensors, right? So this is by definition phi 1 plus phi 2 as a map. What is this map? This is phi 1m plus phi 2m and by S. So So this is exactly phi 1s on S tensor m plus phi 2s S tensor m. Okay, so similar checking. You notice that if you first multiply by some element in S, let's call it lambda to avoid the same repeated notations. Notice this is injective as phi s is totally determined by phi. As phi s tensor m is defined to be as phi m, right? So if this is always 0 for any S tensor m, that implies in particular phi m is 0 for any m to take S equals 1. Okay, we take S equals 1, yes, S is a ring. And so phi is 0. So this is injective. This shows surjectivity. Suppose we have S linear map from S module S tensor m to n. We show that H is phi S exists some phi R linear map. Basically, we put or we construct phi to be the one defined to be right? This is very similar as you just when it is phi s, how do you define phi s over 1 tensor m is m? It's phi m, right? I mean phi m equals phi. In general, here I just for this arbitrary given h, I'm trying to hit it. You use the same method, just and then I check. Firstly, phi are linear. As h is S linear. So phi Rm equals h 1 tensor Rm. In particular, when you are linear, you are S linear. When you are S linear, you are R linear. Because recall this is the case. R, we move it outside, it's just f of R. Think of it as element of S, and so this is f of R h1 tensor, and f of R. This is also just R h1 tensor m, and this is R phi m. Okay, phi is R linear. And then let's check, is phi s equals h, so phi s over s tensor m become the same as h over s tensor m. So they coincide on elementary tensors, so they are the same. And so we are done. So remark. So how to think about this? It should be more or less already obvious. This comes from the universal property just described. So it's kind of a joint pair. But in what sense? You could think of it as a joint pair with forgetful functor. So here it's n is S module, but you forgot it. You just think of it as an R module. This is also called the restriction of scalar, right? And this is as Holmes said, bijective to S module. There is a base extension. First remark, second remark. I'm not going to give a proof, but let's put it, state it at the third part of the exercise. Let M be an R module. And N P be S module. Then there is this S module isomorphism. Base change. The restriction. So this looks very complicated and kind of mixing two things. So before not going to prove it, but let me remark this is actually indeed very closely related with the results we already know. If we take n equals s, then we have what? This is tensor R with s. This is the base extension. And notice s p would be just this module map 1 to whatever element p, this isomorphic to p, and hence this is nothing but the same as what we just proved. Base change is adjoint to forgetful functor. Right. Remark 2. Taking s equals r. So n and p are r modules. Now we have R and tensor and R. Yeah, this is why I say it's very similar, because before we have a joint pair between tensor and home. So now it's only about tensor and home due to each other, adjoint to each other. Okay, so we already know this. Kind of the proof of this third exercise is using these two